Chapter 13, Section 4, starting on page 602, the efficiency of recursion. So, with this, we should write these two tutorials, the one starting recursive fib.java on page 602. But again, we've gone over Fibonacci numbers, Fibonacci sequence. We did it way back when, like chapter 3 or 4. So recursion isn't particularly great for this, but it's a great way to explain recursion to show how it works with a pretty easy trace. So just to remember, I guess we did it in 6-4. So Fibonacci of 1, that just equals 1. F of 2, that equals 1. And then f of n, any sequence after that, is f of n minus 1 plus f n minus 2. Remember, you have to hard code these in, otherwise you'd end up with negative numbers and the thing would keep going. So, recursive fib. It's going to recursively sequence through a Fibonacci sequence by calling the public static long fib int with an n. If n is less than or equal to 2, that is one of these two cases here, return 1, else return the fib of n minus 1 plus the fib of n minus 2, and it keeps going until we get to my base case. So let's run that and see how it works. The program itself is not particularly complex. So there's the tutorial. So I got import the scanner, scanner in, new scanner, enter n, int n, next int, for int I equals 1, I is less than 9. Long fib, call it, and keep going. And long fib is in fact a, this is my recursive method right here. So let's run it and see what happens. Okay. So enter n. We'll do a short one, n of 3. 1, 1, 2. Alright. Try it again with a slightly longer number. Alright, still not that big a deal. Pretty quick. Now 50. 50 you could do in a calculator probably in 30 seconds to a minute. But notice, once you get to like fib of 35, all of a sudden this thing starts bogging down. And I mean, you definitely could calculate up to the fib of 43 faster than the computer can do it. Recursively. Now iteratively you wouldn't be able to keep up. But recursively, this is starting to take a really, really long time. So let's go ahead and see what we got here. We'll time from the next split. So then when it turns 46, we'll time till it takes 47. Alright, so there's 46. We'll start our timer. And all the fib of 47 is, took 23, a little over 20, almost 24 seconds for the computer to do it. This is starting to get ridiculous. So we're actually going to go ahead and kill it. Now, what you should try to do is on your computer, which is probably faster than the old one that's up here in the chem lab with me, see what happens. See if yours is any faster, but it's still going to slow down once it gets above like 35. Okay? So the question is why? Why in the world is this so slow? Well, let's insert the trace messages. So recursive fib tracer, page 604. Alright, so what the difference is that here, entering fib of n plus the parameter n, print exiting fib of n plus return value. So it's going to, every time it enters and opens a new one, it's going to let us know when it exits that particular one. So let's go, I don't know, do a small one, enter n, 4. So even here, you can see that, I mean, the amount of calls it has to make to do 4, it has to do enter n of 1, it does fib of 1, it enters n of 2, enters n of 3, but notice right here, what have we done again? Alright, computers are inherently dumb. Here's n of 2, there's n of 2. Alright, there's n of 2 again. There's n of 2 again. So I'm spending a lot of time doing the same thing over and over and over again, which you don't have to do when you do it by hand. So that's where the problem lies, in that this thing opens up so many extra copies that aren't needed, that it really takes a lot of extra time to do it. So if we were to sort of trace, like the diagram on Figure 2, page 605, fib of 6, what the computer does is you would say that's the fib of 5, whatever that value is, plus the fib of 4, whatever that value happens to be. But the computer can't remember that. So to do fib of 5, it also does fib of 4 over here, and then it does fib of 3 here. Then it has to do a separate Fibonacci of 3 here, and opens fib of 2 over here. This one opens fib of 2 here. This one opens fib of 2 here. This one opens fib of 3 again, etc. So you can just see that this, I have lots of redundancy where I'm doing the same thing over and over and over again. Alright. Now if you look at, for instance, on page 606, loop fib, let's try to run that one. Alright. So loop fib, the program itself is a little bit longer. Not much. It's the one we did in 6.4 essentially. So I have my F1, F2, and at first I have to hard code if n is less than or equal to 2, return 1, else start off everything at 1, and then add the new ones, etc. So let's run this one for fib of 50. Remember, we killed the program at fib of 47. It took so long. Well, that looks more like what you would expect your computer to be able to do. So, while recursion is Fibonacci sequences are great for showing recursion, they're not actually great for actually doing recursion. Okay. Now, sometimes you can always. The question would be, can you always speed up a recursive solution by changing it into a loop? So, usually, almost always, the recursive solution and the iterative or like loop solution run pretty much the same time. Occasionally, recursive solution runs a lot slower, but usually it's a little slower because it does add in some extra steps to the program. Not that you have to write, but adds in some extra steps of its own. So if you look at page 607, there's the iterative solution for is palindrome, and it just sort of sequences its variables, which isn't. It's a little bit faster. Not a whole lot faster, but you know, but it's maybe a little harder to figure out. All right. However, in generally a recursive solution, once you get the hang of it, is easier to understand and implement because all you have to do is to sort of figure out your base cases and go from there. So a recursive solution is easier to understand and implement correctly than an iterative solution would be. For instance, if you want to do the permutation generator that we wrote, that's really hard to do iteratively. I show you in problem 1311, but that's not particularly obvious. It's really obvious. They go, oh, well, I know that I have to just, my base case is if I have a string of one letter, that is itself, and that's, you know, its own permutation if I want it, and then, you know, I can go from there. I can make things smaller and then add each version of those new permutations to my old one to get all my possible combinations. So generally, for complex problems, it's going to run, recursion is going to run a little slower, but might often, in most cases, be easier to figure out.